today I want to talk about one-sided limits. I might have gone over this right before the shelter-in-place took place, uh, but I want to make sure that you guys understand limits in the most thorough way possible. So just to review, what is a limit? So in other words, let's just say I give you a standard function f of x, and we want to evaluate the limit as x approaches a. Well, a limit means as x gets closer and closer and closer to a, y gets closer and closer and closer to some f of a. In other words, a limit is where y wants to go. So if I give you a visual example, let's say I give you y equals 2x, something very, very basic. So let's say I just make this little table. And let's just say I want to figure out the limit as x approaches 3. Well, one strategy is just to plug in values of x closer and closer and closer to 3. So in this, let me just get my pen really quick. So let's say I want to plug in x equals 2.9, 2.99, 2.999. Okay, so x equals 2.9. Come on, red pen. You're not working. Get a different red pen. That's the solution. So x equals 2.9, right? And I'm going to plug in x equals 3.1. So if I plug in x equals 3.1, I get y equals 6.2 because 2 times 3.1 is 6.2. But if I plug in x equals 2.9, I get 2 times 2.9, which is 5.8. Now, that's not close enough. Let's try x equals 2.99 and 3.01. Let me try 3.01. Okay, so if I plug in x equals 2.99, I get 2 times 2.99, or 5.98. But if I plug in x equals 3.01, 2 times 3.01 is 6.02. Okay, let me get closer than that. Let me plug in x equals 3.001 and x equals 2.999. So if I plug in x equals 3.001, 2 times 3.001 is 6.002. And x equals 2.999 would result in y equals 5.998. Let's just use common sense. If I plug in x equals 3, I'm going to get 2 times 3 is 6. So what do we say here? We say that as x gets closer and closer to 3 from the right side, and as x gets closer and closer to 3 from the left side, the limit as x approaches 3 for 2x is 6 because of the intent, right? It's like your little brother or little sister going, I'm not touching you. It's true, they're not. I'm not touching you. But the intent is to annoy the heck out of you. In other words, get y equals 6. So I'm going to come back to this when we get the main idea down. So let's just say, I don't want to spoil it. So let's say we get something different. Let's say f of x is equal to x squared. Let me get my cover really quick. And I graph this. I just put all the points between -4 and +4. So let's say I make a little table. Let's say I want to figure out where does y want to go as x approaches 4. We know we just plug it in and get x equals 4, so 4 squared is 16. So let's just plug it in. So let's try it with this example. So let's say I want to get closer and closer and closer to x equals 4 by plugging in x equals 3.9. And let's say x equals 4.1, because you know what? That's good enough, right? So if I plug in x equals 3.9, I get y equals 15.21. But if I plug in x equals 4.1, I get 16.81. Now the difference between 16.81 and 15.21 is way too big. So I'm going to see if I can get a little bit closer. So let's plug in x equals 3.99. as well as x equals 4.01. So if I plug in x equals 3.99 and I get 3.99 squared, I get 15.9201. Do you see how one decimal place makes a significant difference? And if I plug in x equals 4.01, 4.01 squared is 16.0801. Wow, even closer. Okay, let's say I go one step closer and go x equals 4.001 and x equals 3.999. So I'm going to square both of them respectively, and I'm going to get 16.008001 when x is equal to 4.001. And when x is equal to 3.999, and I'm going to square that, that's going to be 15.992001. Notice that the closer and closer and closer I get to x equals 4, the closer and closer and closer I get to y equals 16. But let's just use direct substitution because we use common sense. When x is 4, 4 squared is 16. So therefore, we can conclude, based on getting closer and closer and closer, that the limit as x approaches 4 for x squared is equal to 16. Okay? That being said, I'm going to go, cover that part up. Where's my cover? There we go. So let's say I want to figure out where does y want to go for x equals -3, just to put it in perspective. So I'm going to do the same old song and dance. I want to get closer and closer to -3. Now remember that the left side of -3 is technically -3.1. And let's say the right side of -3 is -2.9. So let's say I square those respectively. -3.1 quantity squared is positive 9.61. Okay, but let's compare it to x equals -2.9 quantity squared, and I get 8.41. Okay, now that's too big of a range. I can't conclude based on that information. I know. Anyway, moving on, let's say I get closer and closer to it by plugging in x equals -3.01 quantity squared and -2.99 quantity squared. So if I plug them in, -3.01 quantity squared, even closer, 9.0601. Okay, let's say I plug in x equals -2.99 quantity squared, 8.9401 for y. Okay, not good enough. Let's go one step even closer and let's try to make a prediction. So if I plug in x equals -2.999 quantity squared and x equals -3.001 quantity squared, what are the results that I get? So when x equals -2.999 and I square it, I get 8.994001. And when I plug in x equals -3.001 quantity squared, I get 9.006001. You and I both know that we could plug in x equals -3 and get a result. But you know what? Let's plug in -2.9999 and -3.0001. And I could just go on and on and on and on and on. But the idea is you can see the pattern that the limit as x approaches -3 for this function, x squared, is +9. It's the intent. Okay? So let me just check the next page really quick. Now let's take a look at this particular problem. So if I look at y equals x squared minus 3x minus 10 over x minus 5. Let's use this using the technique that we know. We know that there's going to be a problem at x equals 5 because 5 squared minus 3 times 5 minus 10, that's 25 minus 15 minus 10 over 5 minus 5. There's a hole in the graph. So let's just get that spoiler out of the way. You can factor x plus 2, x minus 5 over x minus 5. I wrote that lightly intentionally. Anyway, so let's say this is the graph. So I've given you straight up calculus problems, like evaluate the limit. But this is really what's going on. And if you notice, I just drew you this rough graph really quick, that it's the same exact shape. It's the same, so let me just graph these really quick. Y equals x squared minus 3x minus 10 over x minus 5. And y equals x plus 2 are the exact same line. Exact, two A's, exact same graph, but the only difference between these two graphs is that it is illegal to plug in x equals 5 for x squared minus 3x minus 10 over x minus 5, whereas it's not illegal to plug it in here. But we acknowledge that we are technically graphing this. So this particular hole, where we don't know, wink, 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 where we don't know where that hole is undefined. This part is undefined. But that doesn't mean that we can't get arbitrarily closer and closer and closer to x equals 5. So we're trying to figure out where this hole is. So I'm going to cover up this right column. Let me get my piece of paper that covers up the spoilers. So if I cover up this right column and I approach x equals 5 from the left and the right. So let's say I plug in x equals 5.1 and let's say I plug in 4.9. So I'm just going to be lazy and just do the calculator work on the right. So if I plug this in, x equals 4.9, y would become 6.9. I literally plugged all these into the calculator, and you can too. If I plug in x equals 5.1, I get y equals 7.1. Can you believe that? This monstrosity, I do the top part and then divide it by the bottom part, I get 7.1. Okay, well, let's plug in 4.99 for x and 5.01 for x on the other part. Okay, so if I plug in x equals 5.01, I get 7.01 for y. If I plug in x equals 4.99, I get y equals 6.99. No problem at all whatsoever. And now if I plug in, I'm going to do this one last time, 5.001 for x. What do you think x equals 5.001 is going to be as I'm writing this down? All right. So as I'm done writing this down, let's see if your hunch is correct. Yeah, if I plug in x equals 5.001 into this equation, y spits out 7.001. And if I plug in x equals 4.999, y spits out 6.999. However, let me just plug this part in really quick. Let's say I go right for it. If I plug in 5, I get 25 minus 15 minus 10 over 5 minus 5. Now how... See, that's the fun part of calculus, and I'm laughing because I know what I'm doing. Now, how does the left side get closer and closer to 6.999999999, and the right part goes closer and closer to 7.000000001? And yet, if I actually plug in 5, my calculator just freaks out. It gets me 0 over 0, or a hole in the graph. But using our common sense, this means that the limit as x approaches 5 for x squared minus 3x minus 10 over x minus 5 is equal to 7. Now, the reason why we know that is two reasons. We can factor in x equals 5. We get 5 plus 2, 7. Cool. Fantastic. Or we use L'Hopital's rule, because in case of a 0 over 0, we can take the derivative of the top over the derivative of the bottom, and we would get 2x minus 3, 2 times 5 minus 3 is 7 as well. Anyway, so you get the idea that this is the frustrating part of calculus that I didn't show you when we were having in-person classes. Now, let me show one more example, and let me show this really quick. Let me just denote this really quick. So first things first, we have to designate what we are doing. What we were doing was we were taking the left-hand limit and the right-hand limit. So let's just say I give this graph, and I apologize if it's not the same on both of them. I tried my very best. What this means is when we want to take the limit as x approaches a, we want to figure out where does y want to go as we get closer and closer and closer to a from the left side. In other words, where do we want to go if we were to place a tiny little tracker or a tiny little car on this road from the left side? Okay? So as x gets closer and closer and closer from the left side, where is this particular point or hole? Or where is it intending to be for y? Where is this f of a from the left side? Note that this is the notation. I put it in red because I associate left with red and right with green. So I just want to clarify this, because when I was in high school and when I was in college, I thought this was like a to the negative power. I thought this was an incomplete problem. No, this is not a to the negative power or 3 to the negative power or whatever. That makes no sense. So anyway, this is the limit as x approaches a from the left side for a given function. Okay? And the same concept for the right-hand limit. This is the limit as x approaches a from the right-hand side of a function f of x. So as x gets closer and closer and closer to x equals a from the right side, where does it want to go? I just want to take it on this journey over here, okay? So this is not, I forgot to say, note this is not a to the positive power. This is not a to the positive power. That makes no sense. Again, well, sorry about the squished up positive power part. Anyway, so I just want to make it clear that we are taking the left-hand limit and the right-hand limit. So let me go back to those previous problems. Did I do that? Yeah. So if I go to this part, that means, let me get my multicolored pen. That means that above this divider, we were taking the limit as x approaches 3, okay, of 2x from the left side. So this is the limit as x approaches 3 from the left side. Notice that we got x equals 2.9, y equals 5.8, x equals 2.99, y equals 5.98, x equals 2.999, y equals 5.998, and still the limit as x approaches 3 from the left side got closer and closer and closer to 6. And let's take a look from the right side. The limit as x approaches 3 from the right side of 2x, the limit is, we're going to try to figure out where does y want to go as x gets closer and closer to 3 from the right side. So 3.1, 3.01, 3.001, we're getting 6.2, 6.02, 6.002. We're getting closer and closer to 6. So therefore, the limit as x approaches 3 for 2x is in fact 6. Okay, and go back over here. All right, same thing over here. We wanted to figure out where did y want to go as x got closer and closer to 4, but now we can conclude the limit as x approaches 4 for x squared from the left side was 16. And the limit as x approaches 4 from the right side, right? You look at this diagram, we still got 16. Okay? So therefore, the limit as x approaches 4 for x squared is 16, just by analyzing, tracking from the left and right, where does y want to go? And one last one. The limit as x approaches -3. Once again, I wanted to show you one with a negative in there. The limit as x approaches -3 for x squared right? If we approached x getting closer and closer to -3 from the left side, y got closer and closer and closer to 9. And the limit as x approaches -3 from the right side got closer and closer to +9 as well. So therefore, the left-hand limit and the right-hand limit both want to go to y equals 9. Okay? So if I go to this diagram over here, this is the absolute reason why we need left and right-hand limits, is because if we were to plug in a value of x, in this case, x equals 5 for the graph, y equals x squared minus 3x minus 10 over x minus 5, we would get 0 over 0, which is a big no-no. So the limit as x approaches 5, let me just get this out of the way. I know I said the last one was the last one, but I want to make sure you guys understand this. Okay. So we're going to take the limit as x approaches 5 from the right side, and notice we get closer and closer and closer to y equals 7, even though this direct substitution doesn't work. We get y equals 7. And over here, as we get the limit as x approaches 5 from the left side for this function, we get closer and closer and closer to y equals 7 as well. So therefore, the limit as x approaches 5 from the left and right equals 7. I'm going to give you guys a small breather because I do want to go over this part, so take about 3 minutes. Right now I'm moving my neck side to side right now because even I'm a little bit exhausted. Maybe it's because I've had a lot of coffee today. Anyway, so now that we've cleared this up, we take the left-hand limit to indicate we use this notation, the limit as x approaches a from the left side. This negative does not mean to the negative power. The limit as x approaches a from the right side, we put a little positive sign. Okay, and I use red and green, although you're going to use pencil. But I just wanted to show you that that's what it means. I'm going to take a breather, and I'm going to end it on this. Okay? So, when I was in high school, in 2004, so I looked it up, it was like April 2004, so that was the end of my sophomore year, Mean Girls got released in the movie theater. And so my entire 11th grade, 2004-2005 school year, everyone was obsessed with Mean Girls, and I hadn't seen the movie. And so they were just quoting Mean Girls, like, you know, that's so fetch. And if you haven't seen it, it's a great movie. But I saw the movie in my senior year, so I finally got the jokes. And so I graduated high school in 2006. I was taking PRECALC, and my PRECALC teacher decided to give us a head start into calculus, which is what I'm doing. And all of a sudden, he did this math problem. I'm just making this up. We'll get to the problems like this, so I'm leveling you guys up. I'm trying to get you guys stronger and stronger and stronger. So he did this problem. Let's find the limit as x approaches 3 for this piecewise function. And he basically said, the limit does not exist. And so what the joke about that is, in Mean Girls, there's a scene where the main character is played by Lindsay Lohan. She was a famous teen actress, and the math problem at the towards the end of the movie was this limit problem, and she goes in this very enthusiastic voice and very high, the limit does not exist. And so that was just a catchphrase, and I didn't get it. And then in 12th grade, when he did this problem, he said, very like monotonous voice, he hadn't seen Mean Girls, he's never seen it, and he went, and this particular problem, as x approaches 3, the limit does not exist. And all the girls just started laughing, going, "Oh my God, that's a funny from Mean Girls. That's from Mean Girls. She said the limit does not exist." And this guy, and the guy right behind me was like, I think Lindsay Lohan said this at one point. It's like, this is from a movie, dude. The character said it. I hate to say it, but what's his name? Robert Downey Jr. is an actor. He's not really Iron Man. He's not Tony Stark. Anyway, so that became the running gag for my 11th and 12th grade year, was Mean Girls. The limit does not exist. So, just to close this lesson, what does it mean when a limit exists or a limit does not exist? So, without further ado, the limit exists if and only if the left-hand limit and the right-hand limit can agree. So, if you approach x equals a from the left side, and you approach x equals a from the right side, the left-hand limit equals the right-hand limit means that the limit as x approaches a exists. No exceptions. The left and the right need to agree on where they are meeting. Okay? So, I'm going to do one problem where the limit does not exist. So let's say we want to figure out 1 over 0. We haven't seen this before. Danger, danger, danger. We cannot divide by 0, because if I plug in x equals 0, 1 over 0 is error. Okay? So let's approach. I'll do you one better. Let's get really, really, really close to x equals 0 from the left side. So I make this little table just to show you. This is the classic example of what happens when I approach x equals 0 from the left and the right. And you're going to want to see this because this is awesome. So let's make this table. So I'm going to start with the positive since I'm a positive person. 1 divided by 0.1 is 10, because after all, you just move the decimal place over, you get 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000. And 1 divided by 0.0001 is 10,000. And you can go on and on and on. But you see, oh, that's too many zeros. Anyway, 10,000. So the point is, all I did was just move the decimal place over, and it just exploded. It got closer and closer and closer to 0 from the right side. It just exploded. Well, let's take it from the left-hand side. So let's take the left-hand limit. So as x gets closer and closer and closer to 0, 1 divided by negative 0.1, well, that's negative 10. Oh, let me get back in black. AC/DC, back in black. Negative 10. 1 divided by negative 0.01 is negative 100. 1 divided by negative 0.001 would be negative 1,000. And as x, what is it? One more, sorry. 1 divided by negative 0.0001 is negative 10,000. And you can go on and on and on. You see that if I just move the decimal place over, as x gets closer and closer to 0, it's going to explode and go up. Well, I managed to give you a rough graph for what does this graph look like, roughly speaking, for y equals x, 1 over x. And notice that at x equals 0, they go in two different directions. So I'm going to make a little note to myself. Notice that as I go closer and closer and closer to 0 from the left side, the limit as x approaches 0 from the left side of 1 over x, it goes down to negative infinity. And let's say I go from the right side. Remember, as x got closer and closer to 0 from the right side, the limit as x approaches 0 from the right side of 1 over x, it just exploded to positive infinity. It got huge. But what's the definition of a limit existing? So the limit as x approaches 0 of f of x, the left and the right don't agree, because I can get my green. Let me get my green right here. And I'm going to improvise a little bit. Ooh. I'm going to approach it from the left side and approach it from the right side. And the left and the right hand limit can't agree on where they're going. So the limit does not exist at x equals 0. And I just wanted to get you guys psyched up. So we'll be doing a lot of problems where the limit does not exist.